Hello everyone! Today I would like to present a gravitational time portal between Camana and Rinconada, Peru. The purpose of this exercise is to evaluate the claim that an active bidirectional gravitational time portal is operating between Camana and La Rinconada in Peru. Here we have a photograph of La Rinconada. This is a mining town, and it's the highest city in the world at an elevation of 16,732 feet. And that's 5,100 meters. So we're evaluating time portals, and I just want to bring up, some physicists say that we can move back and forth in distance, but we can't move back and forth in time. And I say, really? Because 100 years ago, Albert Einstein and Herbert Minkowski, who was Einstein's teacher, demonstrated that we live in a four-dimensional space-time continuum, and that one observer's time can be experienced by another observer moving away from that observer or towards. That other observer can see that person's time passage as being comprised of an interval in time plus an interval in space, which shows that time can be converted into space, and space can be converted into time, and vice versa. So this means the space can be converted into time. Means that they're basically the same thing. It's just how you observe them. So to say that you can move back and forth in time, but in space rather, but not back and forth in time, it seems to me like a logical incontinuity, a contradiction. So let's move on here. I think the solution to this is to examine more closely just what we mean when we're saying things. In this case, let's start with, what do we mean when we say we move forward and backwards in distance? So whenever we measure motion, we never measure motion in an absolute sense. For example, when we go to the grocery store and then come back to our house, we might say, oh, we came back to exactly the place we started from. And, if we say, well, do you mean that in an absolute sense? In other words, your house is rotating around the world, the Earth, and at the equator, the Earth is going 1,000 miles per hour in that orbit, circular motion. And the Earth, meanwhile, is traveling 65,000 miles per hour around the Sun in its orbit. And the Sun is somewhere like, I think it's 2/3 the way out on one of the spiral arms of our Milky Way galaxy. And the Sun is rotating with the arm at a very high velocity around the galactic center of the Milky Way, gravitational center. And the Milky Way, in turn, there's a gravitational attractor called the Vega complex, which is pulling the Milky Way. It's accelerating continuously at high speeds and increasing speeds towards the Vega complex. So to say you went out to the grocery store and came back to exactly the same place in any absolute sense has no meaning. That's not what we mean. So what we do mean is that we went out to the grocery store and came back to our local reference cluster of mass, which in this case is our house. So that's what we always mean, and that's what we always have to, when we do our equations or think about it, we have to keep that in mind. So we always measure motion either in time or in space or both, always relative to a local cluster. And let's talk about our, we're going to talk about time portals, and it makes sense to talk about our what we could call it distance machines. If we're going to talk about a time machine, we might as well start with our car, which is maybe a distance machine. Although you'll see, but when we get in our car and we sit while moving relative to a local cluster, which may be our house, of a local cluster of mass, and the motion is not instantaneous, but occurs over a period of time. So we're traveling in space, but we also travel in time on the way. So really, we are transported through distance and also through time relative to the local cluster. And to measure our motion, we thus require accurate clocks in the car, as well as initially synchronized clocks back at the mass cluster that we're using as our reference, and in this case our house. So we'd want a very accurate clock in our house, initially synchronized, 0 time with our clock in our car. And when considering a time transportation machine, or time machine for short, we should then also expect similarly to be able to move forward and backward in time while also moving some distance in space relative to a local cluster of mass. So we're going to also have to have a transportable clock and a clock back at the reference locations, and initially synchronize those clocks. So let's talk about, we were talking about definitions earlier, and I want to be precise so that we can actually check. We're going to evaluate the claim, so we need to know in some specificity, what do we mean by a bidirectional time portal? If we can't agree on what we mean by it, then we can't agree whether it exists or not. So here's the definition that I suggest we operate with. One, definition of a bidirectional time portal. 1. By traveling a distance interval in one direction over a time interval, one goes forward in time by a measurable amount relative to a reference cluster of mass that is identified as the point of origin in space and time. And that's for direct motion in one direction. What if you go backwards in time? Because we're defining a bidirectional time portal. So the second part of that definition. By traveling a distance interval in the opposite direction over a time interval, one goes backward in time a measurable amount relative to a reference cluster of mass that is identified as the point of origin in space and time for the return trip. So in this case, we're going to have 2 points. To really measure bidirectionality in a time portal, you need to have 2 points of reference origins of a cluster of mass. For one for going one direction, the other for going the opposite direction. So with that in mind, let's look at the thought experiment that was performed. First step, very sensitive but long-lasting atomic clocks, 2 of them, were installed inside bunkers, one at La Rinconada at a height of 5,100 meters, and the other at sea level at a height, of course, 0 meters, in the nearby town of Camana, which is on the coast in Peru. Okay, so that here's this clock. We have an atomic clock put in a bunker because it has to last in one location undisturbed for a human lifetime, in this case 80 years for the test. And then a scientific society funded this study, and they enlisted 2 families, one in La Rinconada and one in Camana. And a young child in Camana was attached to a very accurate wristwatch. And I'll show you one right here. See how the buttons, I gotta move them. Atomic clock, very accurate. And meanwhile, another child in La Rinconada. So Camana, that was the first one, was at sea level. The second child was in Rinconada, was also attached to a very accurate wristwatch, the same wristwatch. I'm trying to keep it all very tangible, this whole experiment. And the atomic clocks in Camana and the atomic clock in Rinconada, the big ones, were synchronized with each other initially, as were the two wristwatch clocks, and the two children, and the clocks, all four clocks, of course, together synchronized at the start of the experiment. And an arrangement had been made, this is number 3, with the families at Camana and at Rinconada. The family at Camana was immediately relocated to La Rinconada, and the family at La Rinconada was immediately relocated to Camana. Now, I want to make this so tangible, and I don't want to have some nuclear-powered ship thrusting particles back at the speed of light. You know, every time you introduce something so far out in technology, it distances it from our appreciation of the event. So, let me talk about how these people, these families, include the children, of course, relocated. They loaded up their pack mule with the supplies, and they walked down the mountain road, going down 5,100 feet in the case of going from Rinconada to Camana. And the family in Camana, again, they loaded up their pack mule, and they walked up. It took them like 4 hours or so to get from Camana to the Rinconada. So this is very tangible. It's not high tech. This is the sort of things that humans have been doing for thousands and thousands of years. The only thing that's different in this is that our measurement. We're actually measuring things accurately. So then, step number 4. After 80 years, the child become adult now, 80 years later. Originally from Rinconada, was relocated back to Rinconada. So they walked up originally, the child from Rinconada was relocated back to Rinconada. So we're at Camana for 80 years, and they walked up the mountain with their pack mule again. And the child originally from Camana, who spent 80 years up in Rinconada, La Rinconada, but was originally from Camana, well, they walked down the mountain with their pack mule, and when they got to their location, the clock times from each of the former children, the wristwatches, were compared to the clock times from where they originated. And one origination was in Camana. The other point of origination for the reverse trip was from La Rinconada at 5,100 meters. So what they found when they compared the clocks was that the clock from the child adult returning to Rinconada from Camana, where they spent 80 years, was found to have moved 421,000 meters into the past. So while the child was in Camana, they were going into the past relative to their point of origin in La Rinconada at the height. And 7 and last here. The clock from the child adult returning to Camana, meaning they spent 80 years up in La Rinconada, was found to have moved 421,000 meters into the future compared to Camana. So while they were up in La Rinconada those 80 years, they were moving into the future. It's kind of like driving a car. It's a time portal, though. They're moving into the future. One was going into the past, and the other one was going into the future, that 80 years. Okay, I want to say something about and this is important. It's important detail. Why did the physicists program the clocks, all the clocks, to express the time in meters, not the usual seconds? Well, let's go back to Einstein and Minkowski again. They showed that we live in a four-dimensional space, as I said before. And accordingly, space physicists today acknowledge this. And because of that, they want to put space on the same footing as time. If you're going to measure something, let's say you're measuring two people, and one of them you measure in terms of micrometers, and the other one you measure in terms of, let's say, meters or feet or something, two totally different units, it's not going to be fair, because you say one is 6 and the other is, I don't know, 5,320. Like, it's not good in science to mix things up like that. So in natural units, 1 second is equal to 299,800,000 meters. So close to 300,000 meters, if you want to say it simply. 300,000 meters. 1 second is equal to roughly 300 million. Did I say 1,000? I mean 300 million meters. 1 second is equal to 300 million meters. And this is true in a graphical sense. If I draw momentum on a piece of paper and do the geometric, what do you call it, the proofs and things like that, it's very fun, very easy. Implicitly, the diagrams are balanced, where this one second is going to be naturally equal to 300 million meters. It works out that way. It's not just a definition, it's really an intrinsic expression of an equality, like an identity. So if we express, it's a fact that humans are much more accurate in terms of meters than they are in time, because 1 second is equal to 300 million meters. So, you have to divide a second up into tiny, 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 tiny bits to get it down to a meter. But if you talk in terms of meters, we know what that is. I'll have more to say about that in a second here. Let me move up. So, yeah, it's a good point. And this one's just generally completely not understood, I find. But we're going to explain it here. So the physicists programmed the clocks at La Rinconada and also at Camana to express time in meters rather than seconds. So now we want to talk distance, like altitude, 5,100 meters up. And we talk time in the same meters. So we're balanced. Why would we do anything else? And living in a four-dimensional reality. So this actually makes way more sense. They use meters rather than seconds or light years because people do not have a good feel for seconds. Like, second is such a long thing and you have to divide it up into tiny, tiny parts to get to a meter. So it's very difficult to have any feel for what it is. But a meter is small enough that you can really understand it. And so, also, it's equal to 1 human adult stride, right? And a second is equal to, for most people, it's very close to 1 heartbeat. So we're applying primate physiology units, highly specific and highly biased. We're imposing our primate nature onto the natural world, which doesn't really, it's not scientific. So, in other words, people are extremely insensitive to changes in time, but they're very sensitive to equivalent changes in distance. So when you measure everything in distance, you make it balanced, and you also make it so you can see the units make sense, and you can see any changes much more clearly. So let's go to the next chart, and I want to talk a bit. It's unusual when we talk about physics to talk about human biology and neurology, but in this case, it's actually very, very clarifying to do so. And I'm not going to go into huge amounts of detail, but before a neuron fires, neurotransmitters have to be created and grown in the fluid, and then then vesicles need to be grown, as shown here, synaptic vesicle. And the synapses are long at the end of the axons, and they almost touch. There's a gap, synaptic gas between these axons and the neurons that the synapses are proximal to. So the vesicles grow inside the bulbs here, and that takes time. And then the vesicles are the word transducted or something. They have this little mechanism that walks along on pulling this vesicle towards the cell membrane, where it merges with the membrane, and then it epicytosis is I think it's called, and the neurotransmitters diffuse osmotically across the synaptic gap and then get absorbed into receptors in the the neuron that they're trying to raise the excitation level, and it raises the voltage, And then when it gets enough of these from one neuron or many neurons, it'll fire. Now I have a little note here that generally speaking, a neuron can fire about 200 times per second. Now, that sounds, people listen to people, and they say, "Oh, that's really fast," and then they go on about how the human brain, with its something like 5 billion neurons or something, how it has so much parallel processing that it's so very, very fast. But and this, I'll say one more point, then I want to make another point. The speed of water molecules at 37 degrees C, with like body temperature, is about 1,400 miles per hour. And that's almost 50% fast. I said approximately, but it's getting close. Approximately 50% faster than the rotation of the Earth at the equator. So when I say slow, I'm not being naive and saying, "Oh, these things are not, really clipping along." Ordinary water at human body temperature is vibrating within these small spaces at faster than the speed of the Earth's rotation at the equator, substantially faster. So this is a high frequency oscillation, and really drives our metabolism. That's why when we're at body temperature, 37.5 or something degrees Celsius, and it varies within individuals. When it gets much lower than that, we slow down and our minds don't function. And you only have to go down 3 or 4 degrees, and there's substantial reduction in metabolic capability, and you go into a stupor, then you die. So because these vibrations are intrinsic to all the chemistry and the enzyme activity and all the things that make us a human. And feel there's another topic, whether we are a time machine or not, and that's for another discussion. I want to get through this one first, more than enough to deal with. So there are many people. The view is that these reactions, and I've included the part about the water molecule, as if I'm working against my own thesis, but you'll see when I'm going in a second, which is now. Yes, there is parallelity, and it makes us a lot faster than we would be, and we're not as slow as rocks, and we're faster than a sloth, but we're nowhere as fast as a bird. We're not, nor are we anywhere near comparable to computers these days, in terms of calculations or doing any mental processing. Computers, we go, wow, it does it so fast. It's like it didn't take any time at all. Hundreds of billions of calculations per second. So we are slow compared to ordinary physical processes, and this neuron firing 200 times per second really fires one time every 1,500,000 meters. So it's firing in terms of ordinary physical processes very slowly. And as a consequence of that, we have this enormous bias against changes in time, which we can't detect normally, or even if we do, we see it as so small when it's equivalent to a large changes in length in natural units, which is actually the truth. So let me just say here, estimates for the time processing to for us to process stimuli, in other words, have a reaction, and form a thought discrimination, are typically in the range of about 0.25 seconds. So that's a quarter of a second. And it's not exact here, but we're reasonably close. And humans walk at a rate of about 1 stride every half second. So that's 2 strides a second or so. So a human would naturally be able to associate like half a second with about 1 meter. So, we feel okay with associating 1 second with 1 meter. It seems like we're doing a nice balanced treatment here. But in physical reality, however, half a second is not equal to 1 meter physically. It's physically equal to 150 million meters. So if that isn't a bias, a prejudice, I don't know what is. It's a horrendous prejudice and bias. So we conclude that humans will generally perceive changes in time as being 150 million-fold smaller than they actually are. Expressing both time and space in meters allows us to overcome this extreme bias and to much better express physical truth. So, we don't have to go all through this stuff. We just put the units for time and space on the same footing. Use meters for both. And you don't have to worry about all this stuff. The truth will be revealed. And that's what we're doing. That's what these scientists did. So let's look at the results again, pictorially. Here we have Camana. You can see a beautiful little town on the ocean. And I show a picture from this Google Earth, a satellite shot looking down on Camana. They say Camana, Camana. That threw me off for a while. I thought that was his name, but it's, I guess, some kind of province of Camana, and the town is Camana. Anyhow, there we see it. On the left. Now on the right we see the same picture there, La Rinconada, the mining town. Well, it's not, it's a different one. La Rinconada, the mining town. And I give the aerial satellite view of the town. And see that lake there? That's Lake Titicaca. It's the highest large lake in the world as well. So now you know a little bit more closely geographically what we're talking about here. So, and then with this red arrow, I show that when you go from Camana up to La Rinconada through the time portal, if such a thing exists, you're voyaging into the future according to what the experimental results. And when you start at La Rinconada and use that as your local mass reference, what do I call it, the initial start, your initial point. When you use that in Rinconada and travel down to Camana, you're taking a voyage literally and actually and measurably into the past. That's basically all I want to say on that chart. So let's look again. Oh, here we get into some really good stuff. And I like to explain things because nature's not complicated, but a lot of humans, the way they make things, they use what I call arcane notation, and they always look, if there's an easy way to explain it, it seems like they put it in the closet, hide it. Or I may be wrong on this, so don't take it too seriously, but often it seems that way. But I like to take it and find the way among the billions of ways of looking at it. Find the one that's just so simple, right? Why complicate things? So here we have, this is what The derivation, I wanted to derive an expression for gravitational time dilation. And I want to then do the calculations to verify these results that they found using the clocks. So the first step is to derive these strangely. We'll see why it's so in a little bit. First step is to derive the escape velocity, which I call v sub escape there, for any particular position, height of the Earth's gravitational field. So for any particular radius from the Earth's center of gravity, so some radius in meters, what's the escape velocity? So what kinetic energy would you have to have that if you gave that, like the thing's going sideways at 10,000 miles per hour, I don't know what it is, but we can calculate it. That it just goes round and round a few times, and then it's, the orbit is expanding, and until it's out of the influence of the Earth's gravitational field. So that's what an escape velocity is. And once we do that, and we're not doing it here, I'm just describing the steps. So step 2 is to explain why the escape velocity is relevant to the solution. What the heck does escape velocity have to do with time dilation, gravitational time dilation? Like, when I was initially thinking about this, it seemed frankly crazy. Like, why are you doing this? We'll find out. Again, through a devilishly and may I say cunning way of approaching the problem. And I've never seen that before, but I'm almost positive it's correct. Anyhow, enough of that. Then 3, apply the escape velocity and this other expression, there's an Einstein special relativity that's known as the boost, which shows how lengths under certain circumstances in time and space and even the mass get larger according to special relativity. And there's also what I call the buck. Like boost and buck is known in electrical engineering. Boost makes it higher and buck makes it smaller. So if you flip the boost, you get the buck. Okay? So apply the escape velocity to get the time dilations at the particular distances from the Earth's center. In this case, we want to certainly look at Camana, and we'd certainly want to look at La Rinconada, 5,100 feet above it. But we'd have to, on both, use at least initially, the Earth's radius from the Earth's center. Alrighty, so let's derive the escape velocity in probably the simplest and most direct way ever done in the history of mankind. Here we have it. So, derivation of the expression first, that's what we're doing, then calculation of the results. Okay, 1. And I'm going through the derivation. It's a one-line derivation, which I love when it's just one line. The energy input, the escape velocity, is the energy input required to lift a mass, m, out of a gravitational well. In other words, when you go closer to a planet like the Earth, you're going deeper and deeper into gravity, and it takes more and more energy to get out because you're deeper in. So it's a gravitational well. So the escape velocity is the energy input required to lift a mass out of the gravitational well when the mass is from the initial radius r to the radius which is the effective infinity radius. And I don't want to talk about infinity, but when you get to the point where the amount of attraction by the Earth is so small, it's basically negligible, and that's nowhere near infinity, but it's a manageable distance. That's what I'm talking about, that kind of infinity. So when you lift from a initial radius to r infinity, and people talk about negative and positive energy. Well, when you're doing that lifting, that you're putting positive energy into it. So the expression better darn well be positive. the one I'm using, lifting it, lifting it up. You got to put positive energy into it. So we call that the escape energy. And it's going to be the sum, like an integral is just a sum. It even looks like, the original ones that Newton used to use looked like an S because it's a sum. You chop it all up into little pieces, little dRs, and then you in this case it's the force times the little bit of distance, because force times distance is energy, right? So you break the distances up into little segments, and you're getting a little bit of energy and another little bit of energy. And you work it out all the way from the initial radius to start right up to the radius that's effectively infinite. And that we call it I don't even like that, call it that, but it's sum, right? But call it the integral of FDR. And I say, what is that? Franklin Delano Roosevelt or something? No. And so I have it here. The energy of escape is equal to the integral from r to infinity, specific r, of the force times the little bits of the d delta r's, right? And so, geez, I actually have, no, I don't. The F, the force, I thought I had double the same thing, but no, I don't. The force is the gravitational force, and it's Newton's gravitational force in this case. So we know it's G, Newton's gravity constant, and big M is the mass of the Earth, and little m is whatever mass you're lifting, hopefully not too big, divided by r squared. So that's the F, and the dr is the same. Okay, and now let's perform the integral. You can look it up. It's I'm not going to go through how you do an integral. In this case, it's so simple anyway. But the result is GMM over an effective infinity. Now, when you divide by something huge, like even an effective infinity, that term goes to 0. So you just forget about it. And then you're subtracting, because r is on the bottom of the integral, and you subtract that. But it's negative, so it's a negative of a negative. It works out, which I don't want to talk about that either, except to say it's a positive energy, and we know darn well when we're lifting that damn thing, we're putting energy in there, and it's a positive energy we're putting in. So anyway, the expression then, the final expression on this single line derivation is that GMM over R is equal to the escape energy. Now, it's a kinetic energy that we're talking about. So we all know that 1/2 mv squared is equal to the kinetic energy. So 1/2, we get the 2 on the bottom, it's 1/2 mv squared. And it happens to be the escape velocity. And so now, can you multiply by 2? Okay, so what we got to do here is to multiply both sides of the equation by 2. And then we got to also divide out the m, divide both sides by m. And when you do that, you go from the blue rectangle to the purple rectangle, multiplying by 2 both sides and dividing both sides by m. And what we get is what we wanted. Find the escape velocity. There it is. V squared escape is equal to 2gm over r. Now, in the Buck expression, it has a v squared in there. And it turns out that we leave it as v squared because that's what we want. Why take it down? Why do the square root? And we're going to insert that directly in the Buck expression. Now, we found the escape velocity. That's, what was it, step 2? And step 3, I think. Do I have to go back? I think I do. Sprain, escape velocity. Yeah, okay. Yeah, 2. We're in step 2 now. We found it. That was the first step. There's escape velocity. Now we ask the question, what the heck does this have to do with gravitational dilation? So here we go. Okay. So I'm going to come at this, like I said, in a deviously cunning, kind of tricky way. But it's going to simplify everything. So to answer that, we have to put ourselves in the frame of an object just starting to fall to Earth. Like it's at that our effective infinity where it's small, but it's still creeping, pulling that object. And the object that we're going to talk about is a spaceship. Okay. Now let's perform a thought experiment. I'm reading from it. And let that object be you, floating in deep space in a small, closed spaceship with no windows. Now, why I say small spaceship is because the attraction is going to be to the gravitational center. So if it was a huge anything, there's going to be an angle, right, between the angle center. Let's say if you were 200 feet long, your head would be pulling in this direction, and boy, I have trouble here, and your feet would be pulling in this other direction. So you'd be getting tidal forces going on. But if it's a reasonably small ship, everything's parallel. Can I do this? Yeah, parallel. So we're going back to this thought experiment. So let you be that object floating in a deep space, effectively separated from the Earth's effect of the Earth's gravitational field, but just drifting into it. The spaceship has no windows, so this is like Einstein's thought experiment, where he's in an elevator, and there's a rocket pushing up at 9.81 meters per second per second. In other words, the gravity at the Earth's surface. And Einstein says there's no experiment you can perform inside that elevator that would allow you to distinguish being actually on the Earth, in the elevator, being pulled down by the Earth's gravitational field, or being in a rocket. You can't distinguish, the rocket pushing you up at that 9.81 meters per second per second. You can't tell the difference by any experiment. So Einstein said, I'm going to say there's an equivalence principle here, that you can't tell the difference because there is no difference. And this proves, he says, that gravity is an acceleration. Okay, gravity is an acceleration. Like you are you. It's an identity. So we're going to do the same thing here. So you're floating in the ship, and the ship is drifting. Now you start falling faster and faster. But I said that, not you, because you're floating in there. Nothing's changed. So, and no experiment that you perform can tell you that you're what we might call falling in a gravitational field, because you're just going on a geodesic. You're going as straight as you can go. No change. So, okay, when the ship has fallen to near the radius r, like, I want to put in this detail because we have to soft land on, let's say, Camana. We've got a soft land on Camana, and I don't want the guy in this spaceship to know things and use his mind. I want him to accept in any other way than to tell us what's his experience or her experience. What their experience would be is that nothing has changed until just at the moment when that spaceship detects that it's going to have a collision and fires the little rockets, and it accelerates upward because it's coming in at that point at the escape velocity, because that energy is transformed from potential energy into kinetic energy, and it's 1/2 v escape squared. So what the person in the ship which is you, will use the accelerometers. They got those little stress detectors. That they calculates the accelerometers. You'll detect that you've been given a force large enough and long enough to bring you up to the escape velocity faster than you were going before. So you've been accelerated by up to v escape. And you will deduce, because you know special relativity, that your time has slowed down at the time dilatation according to the relativistic buck, the inverse, according to the relativistic buck expression. So now it's interesting because it soft lands. And the people in Camana rush forward and they're looking at this spaceship. And the guy's in there, he's just finished this calculation. And he walks, the door opens and he walks out onto the beach. The people around there. And the people say, tell us about your trip. Tell us about your trip. What is this? And the guy's a nerd, like many people. And he says, he's wants to talk about his recent experience, literally. So he says, well, I was floating in my spaceship and nothing happened at all until just a little while ago. And I calculated that I went from having zero velocity, relative to my situation, to being accelerated enough to bring me up to this v nu. He doesn't know it's the escape velocity necessarily, to this new speed. And he said, my time has, according to special relativity, has to have dilated this specific amount. And so the people on the beach say, well, you're in our local frame, our local town. Let's say, maybe they don't put it as local frame, right? So if your time is dilated, doesn't that mean that our time is dilated? And the guy says, yes, because I didn't do anything after I was accelerated. I opened the door and I walked out. So, but let me tell you what it means. It means compared to the space where I came from, outside the influence of the Earth, my time has been slowed down by this amount. And we're going to calculate it next. He calculated it, and he says, there's no experiment I could have done that could tell the difference from what I experienced from anything else, Just like Einstein's experience in the elevator. It's according to the equivalence principle. So we know from my recent experience that how much at this location time has been dilated. And I have my calculation, I'll show you. So he showed them the calculation, and all they wanted at that point was probably to go lie down and have a nap or something. But we're going to look at this. So we went through this. We went through, does this have to do with time? Yes, yes, yes. And this, okay. I actually went through a lot here. You would have expected time slowed down. Okay. So I'll go over this. We have our expression we derived, and we say to land at the radius r, you will need to be accelerated upward enough to increase your velocity upward, enough to cancel out the downward velocity. In other words, if you don't do that, you're going to create a little meteoric crater on the surface of the Earth. So this will be the first time you felt any forces in time to spaceship. Yes. In your frame inside the closed spacecraft, you could measure that you were accelerated. Yes, yes, yes. And you'd use this expression here. T primed is equal to T local times 1 minus the escape velocity squared. And we already worked it, see on the top there, V escape squared. We know it's 2gm over r, right? Divided by c squared to the 1/2. That is the Buck expression. So we're going to, because we proved it's equal to gm over r, we stick that in there, into the Buck expression. T primed, which is the one that was accelerated, how its time has changed. And now we know that when you go down in a gravitational field, you're accelerated in this way. That result will be 1 minus 2gm over rc squared, all to the 1/2, which is the square root. That's the Buck expression. So we derive that. So now we know how to calculate the time dilation at any radius from the Earth's center. So we can do it at Camana, we can do it at La Rinconada. We can take the two that we find and get the difference between the two, and we get the aging difference, in the time portal. So on the bottom here it says, let's use this result to calculate the time dilations at different radiuses from the Earth's center. move up here. Oh, I see I went the wrong direction. Oh, good, 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 good. And there we go. So this looks like a busy chart, but much of it you just go, yeah, you know, let's look at the result. And then color coded and stuff. So here we have one. The relativistic buck for slowing down time is given by, and I have the expression. And then I have also a link. If you use that link that I have there in blue, and it'll take you to the first one of my general relativity series of five presentations. And this first one I derived geometrically in a very wonderful, simple way, special relativity. And so this Buck expression was one of them. And if you want to see one of the simpler ways of getting at this, look at charts 17 through 23 at that link. But since I did it there, I don't think we'll be wasting our time here if we do it here as well. So let's move on. So I've written down the relativistic Buck expression. I color coded it. G is now that purple color, M is green, R is orange. So when you see the numbers there, you know what they refer to, like this 6.67 times 10 to the minus 11. That's purple, so it's going to be a gravitational constant. And the other number is going to be mass. And the R is going to be the orange number in meters. You know, that in the first Camana, which is sea level. And then the other one's going to be a slightly larger one, if you look at his, at La Rinconada. So great. So we go in Excel because it has a long enough buffer for numbers after the decimal point to be able to do these calculations. Your calculator, you might be frustrated depending on your calculator. So I used Excel, put the numbers in, and what I get is that the and then I multiplied. You got to make sure you get the units right. At the end, you want meters, right? So you got to take the you got to convert the seconds to meters by going to the speed of light. That's that 299,800 thing. And then you got to convert seconds to hours, and then hours to days to hours, and then hours to seconds. Blah blah blah. And so you look at that. That's all I've done. Cancel, cancel, cancel. You end up with meters. And lo and behold, at long last, but not too long, we come up at that the difference in time over the 80-year duration was 421,000 meters. So that's not an insignificant amount. Yeah. And the bottom, I summarize what that means. We just corroborated that over the 80-year period, the child become adult that moved from La Rinconada to Camana, so in other words went down, traveled 421,000 meters into the past relative to their place of origin. Now, if you're traveling, let's say you had a twin and you went into the past, you're going to see that the twin is younger. Let's see. You go into the past. You started at Rinconada and went to Camana, and then back to La Rinconada. Camana at the time goes more slowly, so you're gonna be younger. And then the child adult that moved from Camana to Rinconada traveled 421,000 meters into the future relative to their place of origin, which was Camana. So because when they're in Rinconada, the clock is going faster, so they're older than their twin. They've traveled into the future. So here we are. Now we go and we look. There's another interesting point, and I don't want to dwell on this too much. But we just worked out a very accurately, and I think it's applicable, and in a way that's applicable. The time changes in going up to La Rinconada, and the time to change going down from La Rinconada and back in both cases. But we've done that accurately. And you might say, well, that's 5,100 meters. Well, and it's like, what would happen if you went into deep space at R effective infinite? And I just want to give a glimpse on this. Now, one of the problems is that the Earth is actually rotating, and it makes the calculation a little longer, and it's not worth it for this. But I just want to show just from the gravitational effect alone. So I'm going to say, if you were to spend 80 years in a colony at rest with respect to non-rotating Earth, so let's just say it wasn't rotating, to simplify it for the moment, and you went to deep space, and I say that after 80 years, the colony would be in the future ahead by about 500 million meters. 500 million meters. Now that's not a negligible amount. And this is almost twice the distance from, it's not twice, but it's close, approaching twice the distance from the Earth to the Moon. So try jogging that, you know. So, and I did the same method that we just did, and so I don't want to go over it again. But that seems to be some kind of limit to what you can do with the Earth's gravity. And if you want to go with a stronger time portal than that, to get a larger effect, you need to increase the gravity. Go to a more massive planet, for example. So now we've done the test, we know what the results were. And I want to match our results against our initial definition, because we're not proving anything if we don't nail it down to what we meant when we started. You know, if you say, is there a zebra in New York? Well, if you go and you find a horse, that doesn't prove anything about the zebra. And if you find a zebra and somebody else thinks you're talking about a horse, that doesn't prove anything. So we have to go back to the exact initial definition. That's why I did it. And just see, do we really have a bidirectional gravitational time portal here? I mean, that sounds kind of far-fetched. Or not. So we look at the definition of a bidirectional time portal again, and we get what we used before. And we ask the question, yes or no, for every aspect of the definition. So I'm starting now. Let's check the definition. First bullet. By traveling a distance interval, change in distance, in one direction. Yes or no? Yes, we went from Camana to La Rinconada. Okay, we're breaking the forward direction and back direction, so we'll get to the other way in the next bullet. Okay, the answer is yes. Direction, yes. Okay, over a time interval, yes. We spent the walk plus 80 years. Yes, okay. One goes forward in time by a measurable amount. Yes, we did the experiment and we went forward 421,000 meters. Relative to a reference cluster of mass that is identified as the point of origin in space and time? Yes, we went from, after we spent 80 years in La Rinconada, we went back to Camana, and we checked the clocks there. So we went back to the relative to the original point. Yes, we went back, okay? Now let's talk about going the opposite direction. And look at this. By traveling a distance interval in the opposite direction, yes or no? Yes, we went from, the first one was from Camana up to La Rinconada. The other one went from La Rinconada back to Camana. So yeah, opposite direction, yes. Over a time interval, yes. The walk plus 80 years. One goes backward in time by a measurable amount. Yes, we were able to measure it. Relative to a reference cluster of mass that is identified as the point of original origin in space and in time. Yes, we measured the wrist clock and the original clock and the bunker there, yes. So yes. Yeah, so what we conclude from this is that according to our original definition, very precise, and our experiment, hopefully equally precise, the region of space-time from Camana to La Rinconada, Peru, including the endpoints and cities at each end, has been tested and found to satisfy all the requirements listed in our original definition for defining a bidirectional time portal. And so we have to conclude that this region is a bidirectional time portal according to our definition. So holy cow, it really is, according to our definition, an active bidirectional gravitational time portal between La Rinconada and Camana in Peru. So here's our conclusion coming up. Scientists were able to test and validate that a fully functioning bidirectional time portal exists between the towns of Camana and Rinconada, Peru. What they found was a person moving from Rinconada to Camana was able to move backward in time by 421,000 meters relative to their place of origin over a period of 80 years as measured by very precise atomic clocks. Likewise, a person moving from Camana to Rinconada, in other words, the other direction, was able to move forward in time, again, the opposite direction in time, by 421,000 meters relative to their place of origin over a period of 80 years as measured by very precise clocks. Last point. These results definitively prove that even without any equipment, other than the ability to walk, humans are able to move significant distances forward or backward in time with respect to their points of origin, I might add at will, on planet Earth using existing gravitational portals here on the planet. So, something to think about. And I want to say thank you very much. You know, I really, really enjoyed presenting this. I hope you enjoyed it. I hope you get a little bit of light in your eyes and dazzle with that. Really, not about nothing to do with me or the presentation, but our marvelous planet. I mean, when you take the blinkers off and just look at what's really there and what's really going on. I mean, there's not much that's mundane about this voyage of adventure that we're on here, on this very mysterious and immensely wonderful planet. So I enjoyed presenting this very much, and I hope you got a feel for that out of this discussion. And with that, I want to say thank you very much. I'm checking out here. Bye for now.